All right, what is up, party people? Okay, so what we are going to do today is behavior of sound waves. But before we get into that, I just wanted to do a quick little review with you. So this is the stuff that we did the other day. If a ship captain sounds a foghorn towards an iceberg and hears the echo, here's the echo. 4.6 seconds later, how far away is the iceberg if the air temperature is negative 10 degrees Celsius? All right, so what we are looking at is just another one of our velocity problems, right? So we're looking at how far away the iceberg is. So hopefully you are thinking about displacement now. So how far away? All right, so we are given a time, also 4.6 seconds, but the time is an echo. So think about what an echo is. So an echo is a sound wave going to the iceberg and then coming back. All right, so what this 4.6 seconds is telling us is that is that's the time that it took the sound wave to go to the iceberg and then back. Well, we don't want to know that. We just want to know how far it is away. So what we're going to do is we're going to take this 4.6 seconds and divide it by 2, which gives us 2.3 seconds. Okay, so the last thing that we have to figure out is our velocity. So the velocity of our sound wave. Now we are given a new temperature of negative 10 degrees Celsius. So we have to remember that our sound waves are going to change speed in different temperatures. So let's recall our new equation. We have 331 meters per second, and that is the sound of, or the velocity of a sound wave at 0 degrees Celsius, plus 0.6 times our degrees. All right, now this is a negative, so we still have to take that into account. So that's going to be 331 plus a negative 6. So it's just like saying minus 6. Okay, so 331 minus 6 gives us 325 meters per second. Okay, so that should make sense because remember, at room temperature, 20 degrees Celsius, the speed of sound is 343 meters per second. So we have decreased the temperature, so we've taken out heat, taken out kinetic energy. So our 325 is way lower than this 343. All right, so now that we have all of our variables, we can go ahead and solve for our displacement. So we know that velocity is equal to delta x, our displacement, over delta t. Well, we're solving for delta x, so we want to get rid of delta t. So we are going to multiply it on both sides. So delta x is equal to our velocity times our delta t. So we've got 325 times 2.3, which does give us 747.5 meters. So that iceberg is 747.5 meters away. All right, let's keep moving. All right, so we're going to be talking about the behavior of sound waves today. So just a couple of little things that sound waves do. The first one that we are going to be talking about is the Doppler effect. So every single person has experienced the Doppler effect before. So what the Doppler effect is just an observed, once again, an observed or apparent change in frequency, all right, of a sound wave when there is relative motion. So there's got to be motion between the source of the sound and some observer. Okay, so the object that is making the sound has to be moving and the observer is going to notice it. All right, so one thing that I do want to just kind of beat into your heads for this one is that it is an apparent change. All right, so think about if you are, so where you have mostly seen this is in like an ambulance coming towards you, or a fire truck, or a police officer coming towards you with their sirens going. All right, so that sound that is being produced is not changing frequency. All right, what is changing is the distance between you and the source of that sound. All right, so because the distance is changing between you and the source of the sound, you are going to experience, once again, an apparent change in the frequency. So remember, the frequency, a change in frequency, is what gives us our high-pitched sounds and our low-pitched sounds. All right, so we're going to look at this. So we've got a police officer down here. All right, he's got his siren on, and he's coming towards this young man right here. Okay, so notice, let me erase this part. So notice that as he is coming towards this person, the waves are getting short, the wavelengths are getting shorter and shorter and shorter. All right, so remember, those wavelengths are decreasing. Well, wavelength and frequency have that inverse relationship. So as the wavelengths decreases, the frequency is going to increase. So what does an increase in frequency mean to us and how we perceive it? That is going to be a higher pitched sound. So it's going to be a higher pitch. Now, this same police officer, same siren, just passed this young lady over here. And so he is going away from her. Well, as he is going away, those wavelengths are getting larger and larger and larger. So the wavelengths are increasing. Well, that means that our frequency is decreasing, which means that we hear a lower pitch sound than as it was coming towards us. All right, so this is why you hear those differences. So if you think about an ambulance or a fire truck or a police officer with its siren on, you hear that higher pitch as it's coming towards you instead of as it's going away, because as it's leaving, you hear that lower pitch until you really can't hear it anymore. Okay, so this is one of my favorite videos to watch, and I'm hoping that it pulls up.
Hey, Sheldon, there's something I want to talk to you about before we go to the party.
I don't care if anybody gets it. I'm going as the Doppler effect.
No, it's not.
If I have to, I can demonstrate. Meow. So what time does the costume parade start?
The parade?
Yeah, so the judges can give out the prizes for best costume. Most frightening, most authentic, most accurate visualization of a scientific principle.
Oh, Sheldon, I'm sorry, but there aren't going to be any parades or judges or prizes.
This party is just going to suck.
Oh, come on, it's going to be fun, and you all look great. I mean, look at you, Thor, and oh, Peter Pan, that's so cute.
Actually, Penny, he's
Hi,
wrong.
Peter Pan!
I got a handful of pixie dust with your name on it.
No, you don't. Hey, what's Sheldon supposed to be?
Oh, he's the Doppler effect.
Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Say that again.
It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Just so you get it.
It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Oh, sure, I see it now, the Doppler effect. All right, I got a shower. You guys, make yourselves comfortable.
Okay.
See? People get it.
Hi.
Hello.
So So what are you supposed to be?
Me? I'll give you a hint. Meow.
Choo-choo train?
Close. Meow.
The brain damaged choo-choo train?
All right, so that's as far as we'll watch today. But the sound that he makes, that's what like you would hear at, say, a race car track or something like that. So that is the Doppler effect, or a train going by. You hear that higher pitch frequency as it is coming towards you than when it's moving away. All right, so this is what we just said. So the pitch is higher coming towards you and then drops whenever the vehicle moves away. So you do hear that higher pitch sound as it's coming towards you, like what's happening right here, than it does as it's going away from you, as it's happening right here. Okay. So let's look at a little example of this. There's no math in this. This is very just conceptual. Suppose you are standing on a platform by a train station. As the train approaches the station, it gradually slows down. During this process of slowing down, the engineer sounds the horn at a constant frequency. So constant frequency of 300 hertz. What pitch or changes in pitch will you perceive as the train approaches you on the loading platform? All right, so please excuse my drawings. All right, so first of all, we've got the train. This is my train. There we go. All right, so this train is approaching us. So even though it's slowing down, it's still approaching us. So as it's approaching us, those waves get closer and closer and closer together. All right, so the frequency is going up. So as it's approaching us, we are going to hear a frequency that is greater than 300 hertz. Okay, so that 300 comes from that constant frequency that he is putting out. All right, so it's going to be greater than 300 hertz as it's coming towards us. All right, well, after it comes to a stop, then nothing is moving. The source of the sound is not moving. We are not moving on the deck or on the platform. So what would we hear? What frequency? Our frequency would be equal to 300 hertz at this point. Now, I didn't ask you about this, but it should make sense too. What if it starts again and it goes away? So at that point, you would have the train going away from you, so those wavelengths would get larger and larger and larger, which means our frequency would get smaller and smaller and smaller. So our frequency that we would hear at that point would be less than 300 hertz. I hope that makes sense to you. If it doesn't, then we can talk about it later. All right, but it's just the apparent change of the frequency. I can't stress that enough. It's just an apparent change. So the actual source of the sound, the frequency that it's putting out is not changing. So that police siren, that police car is constantly putting out the same frequency. But because the police car is moving towards an observer, the frequency is apparently changing. So you get that higher pitch coming towards you and lower pitch as it leaves you. The next thing, this one is super cool, that we're going to be talking about is a shock wave. All right, so these are awesome things. You've probably seen them if you've ever gone to see the Blue Angels fly, anything like that. So this is what happens when we approach and surpass the speed of sound. All right, so shock waves are produced when the source either moves at the same or faster speed than the speed of sound. All right, so what is happening? And once again, do not judge my drawings. All right, so we have this plane. Oh, Lord, I'll get used to that. All right, we have this plane. That's our plane. That's the front of our plane, okay? So this plane is going super, 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 super fast, okay? So it's got all of these waves bunched up, all right? High pressure because it's got so many waves bunched up. All right, well, these waves are going to, so they're going to continue around the plane. And as they go to the back, remember, it's going away from that area. The wavelengths are going to get larger and larger and larger, meaning you have super high frequency up here, super high pressure up here, and then super low frequency and low pressure back here. Okay, so that is what is really, really happening right there. All right, so your sound source is going to be this leading edge of the plane that we see right here. So that's your sound source. All right, and it's bunched up at the front of the plane. All right, so what happens is as this plane, so what it's doing, you have this super high pressure in front, and then you've got low pressure, like really, really low pressure happening at the back. So what happens, all right, is that area of really, 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 really high pressure that's at the front of the plane is being followed by an area of really, 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 really low pressure. So what's happening is that pressure is changing so fast that it creates something called a sonic boom. So that's what you see. That's a sonic boom. All right, and that sonic boom is caused by that change, that very, very quick change in pressure. So you've got the super high pressure at the very front of the plane and then the low pressure at the back of the plane. So it's changing pressure really fast. So it creates that sonic boom. Now, the sonic boom itself is not like a sign that it's traveling, that it's the moment. So excuse me, let me get my words straight. The sonic boom that you see, so that little puff of air, is not necessarily shown the moment it overcomes the speed of sound. All the sonic boom is showing is it's just a sign that that plane is traveling faster than the speed of sound. It doesn't happen right at the exact moment that it surpasses the speed of sound. It's just a sign that it is traveling faster than the speed of sound. So a lot of people think that it is produced right at the exact moment when it does surpass it, but that's not the case. It's just necessary. It's just a sign that it has surpassed it. All right, and then the last thing that we're going to be talking about, we're really going to be talking about this more in music next week, but resonance. All right, so resonance is a frequency of a force applied to a system that matches the natural frequency of a vibration. All right, so all objects, every single object has a natural frequency that it vibrates at. All right, so what this is saying is that if you were to strike an object with the same frequency as another object's natural frequency, that second object would start moving. Okay, so it results in a larger amplitude. All right, so more energy, larger amplitude. We're not really going to talk about this glass because you're going to watch a Mythbusters later on about that. But I do want to bring your attention to the girl on the swing and then this pendulum set right here. So what resonance is, so say that you have a swing set. So you have multiple swings beside this sweet little girl swinging on the swing set. Well, there doesn't have to be a person in those other swings But if this little girl reaches the same frequency at which one of those other swings naturally vibrates, then the other swing would start to swing back and forth. All right, same thing with this pendulum set right here. All right, so if we were to start swinging this pendulum back and forth, it would eventually match up with this bob, and this bob would start moving right along with this one, even though we did not start this motion physically. So it was the resonance on this pendulum that made this pendulum start moving. So like I said, we are going to talk more about resonance whenever we talk about music. But right now, what I want you guys to do is to go to the Google Classroom assignment, and I want you to watch the video. It's the Tacoma Narrows Bridge video. I want you to watch that video. Hopefully it doesn't make some of you too sad. All right, but I want you to watch it, and then after you watch that, you're going to do the sound worksheet. So if you have any questions, I will be more than happy to answer them whenever I get back. Y'all have a wonderful day.